Welcome back. In this module, we are going to have a discussion on stacks and queues. The linear list and linear arrays allow us to insert and delete elements at any place in the list. But there are some situations when we want to restrict the entries to be added or deleted only at the beginning or at the end. By restricting the manner in which entries of a list are accessed, two special types of list are obtained called stacks and queues. A stack is a list in which entries are removed and inserted only at the head. The head of the stack is called the top of the stack. The tail of the stack is called bottom or base. A queue is a list in which entries are removed only at one end and new entries are inserted at the other end. The end at which deletion occurs is called front, and the insertion of the new entries are done at the end called rear. The stacks and queues and their implementation are discussed below. Stack. A stack is a data structure in which addition and deletion of elements always takes place at the same end. That end is referred by top. This can be compared with a stack of plates or folded towels where every new item added to the stack is added at the top of the stack. The two operations that can be possible to a stack are given the names push and pop. Push is the operation of adding a new item to the stack and pop is the removal of an item from the stack. That is, first item removed from the stack will always be the last item added to it, and hence the name last in first out or LIFO. When new items are added to the stack, it grows at one end, and if the items are deleted from the stack, it will shrink at the same end. These are shown in the following figure. Operations on stack. The commonly implemented operations on stack are push and pop. Push allows adding an element at the top of the stack and pop allows removing an element from the top of the stack. There are different methods to implement a stack in programs. The general structures used are arrays and linked list. Stacks as arrays. An array is used to store ordered list of elements. So, it is very easy to manage a stack if it is implemented with an array. But in the case of an array, the size of the array should be specified at the beginning. That is, the array is static or its size is fixed. But stack will not have a fixed size. It may change as and when the elements are pushed or added and popped or deleted. A possible solution, even though it is not optimal, is to declare the array with a size large enough to manage a stack. Thus, the stack can grow or shrink within the limited space. The program to implement a stack using an array is given below. Class stack. Private int a of 10 int top. Public stack initializes data member top equals -1. Void push in item adds an element to the stack. If top equals 9, cout stack is full. Return top plus plus a of top equal to item. Int pop removes an item from the stack. If top equals -1, cout stack is empty. Return null. Int temp equal to a of top. Top minus minus return temp. Void main stack s dot push of 2, s dot push of 6, s dot push of 15, s dot push of 22, s dot push of 18, s dot push of 95, s dot push of 76, s dot push of -28, s dot push of 30, s dot push of 20, s dot push of 25. In data equal to s dot pop. Cout item popped data. Data equal to s dot pop cout item popped data. Data equal to s dot pop cout item popped data. Data equal to s dot pop cout item popped data. The output stack is full. Item popped 20, item popped 30, item popped minus 28, item popped 76. Explanation. In this program, a class stack is defined with push and pop as member functions. These functions are used to add and delete elements to and from the stack. The actual storage for stack elements are in the array A. The data member top always point to the top of the stack or the top index of the array. Every time a new member is added, top will be incremented by 1, and every time an item is removed, top is decremented by 1. At the time of addition, stack or array is checked for space. If the addition is not possible, it will give the message stack is full. When the pop function is called, it will first check whether there will be any elements left in the stack to be popped out. If the stack contains no elements, it will give the message the stack is empty. In main, push function is called with 11 elements, and since the array is of 10 elements, 11th element would not be added to the stack. Stacks as linked list. The basic limitation for a stack as array was the size cannot be increased or decreased after declaring it. Thus, either too much space or too less space for an array is reserved. This problem is eliminated if the stack is implemented using a linked list. The stack can be represented using a singly connected list. Each node in the list contains the data and a pointer that gives the location of the next node in the list. The pointer to the beginning of the list is interpreted as the top of the stack. A linked list representation of the stack is given below. A program to implement a stack using linked list is as follows. Class stack. Private struct node, structure to contain data part and link part. In data, node star link. Star top. Public stack initializes data member, top equals null. Void push int item, function to add node to the stack. Node star term equal to new node. If term equals null, cout stack is full. Temp data equals item, temp link equal to top, top equals temp. Int pop, pops an element from the stack. If top equal to null, cout stack is empty, not star temp. Int item, temp equals top, item equals temp data, top equals top link. Delete temp, return item. Destructor stack, if top equals null, return, not star temp, while top not equals null, temp equals top, top equal top link, delete temp. Void main stack s. S dot push of 28, S dot push of 35, S dot push of 3, S dot push of -1, cout item popped S dot pop, cout item popped S dot pop, cout item popped S dot pop. The output item popped -1, item popped 3, item popped 35. Explanation. Here also a class called stack is defined with a data member top, which is a pointer to the structure node. Initially, top is null, indicating that stack is empty. The function push creates a new node whenever it is called. Since memory is allocated dynamically, it will go on creating new nodes as far as memory is available. But when there is no memory to allocate for a node, temp will be null, indicating that the stack is full. The top always point to the new node in the list. In the pop function, stack is checked for items. If the stack is empty, it will give a message stack is empty, and otherwise the topmost element is retrieved and that node will be removed from the list. The calling of push and pop are shown below. When the pop function is called, the item at the top will be removed. If the stack is empty will be displayed. Applications of stacks. The stacks are usually used for the evaluation of arithmetic expression. An arithmetic expression consists of operands and operators. High-level language expression consisting of operators and operands are effectively evaluated with the help of stacks. Quicksort, a type of sorting algorithm which incorporates the divide and conquer rule, is implemented using a stack. Recursion is an important concept in computer science. Suppose P is a procedure containing either a call to itself or a call statement to another procedure that in turn calls the original procedure P, then P is said to be a recursive procedure. This recursion is implemented using stacks because the last value stored should be processed first. Queues. Queue is a list in which entries are removed only at the head called front and new entries are inserted only at the tail called rear. A real-time example is a queue of people waiting to pay the electricity bill. The person at the front be served first, whereas the new arrivals will step to the rear of the queue. In contrast to a stack, the first entry added in a queue will be the first one to be removed from it. Hence, it is called first in, first out or FIFO structure. The name queue comes from the everyday use of the term. Pictorial representation of a queue is given below. Queue is used more than stacks in computer. During the execution of jobs on a computer, one should wait for its turn before accessing some device or process. There will be queues of tasks waiting for printer or disk or CPU. A queue can be represented either using an array or a linked list. Operations on queues. Most common operations possible with queue are insertion at the rear and deletion from the front. Since queue is a linear list, it can be implemented with arrays and linked list as we did with stacks. Queues as arrays. Representing a queue as an array suffers from the same problems of representing a stack using array. An array can store a fixed number of elements, whereas the queue changes its size as elements are added or removed from it. A C++ program to implement a queue is given here. Class queue, private in array of 10, in front rear. Public queue initializes data members, front equals -1, rear equals -1. Void insert queue, int item, adds an element to the queue. If rear equals 9, cout queue is full, return. Rear plus plus, array of rear equals item, if front equals -1, front equals 0. Int delete queue, deletes an element from the queue. Int data, if front equals -1, cout queue is empty, return null. Data equals array of front equals 0, if front equals rear, front equals rear equals -1, else front plus plus, return data. Void main queue queue. Queue dot insert queue of 24, queue dot insert queue of 19, queue dot insert queue of 38, queue dot insert queue of -53, queue dot insert queue of 45, queue dot insert queue of 37, queue dot insert queue of -43, queue dot insert queue of 32, queue dot insert queue of 90, queue dot insert queue of 3, queue dot insert queue of 59. Cout item deleted is queue dot delete queue. Cout item deleted is queue dot delete queue. Cout item deleted is queue dot delete queue. Cout item deleted is q dot delete q. Cout item deleted is q dot delete q. The output q is full. Item deleted is 24. Item deleted is 19. Item deleted is 38. Item deleted is minus 53. Item deleted is 45. Here a class called Q is defined with two data members, front and rear. These are used to keep track of the two ends of the queue. The initial value of front and rear are set to -1, indicating that Q is empty. Two functions called insert Q and delete Q are implemented for addition and deletion of elements respectively. Each time an element is added to the queue, the value of rear is incremented and new item is stored. When the value of rear reaches its maximum value, the queue will be full. At the time of adding an element for the first time, front is incremented and set to 0. Afterwards, whenever an element is deleted from the queue, it will remove the item pointed by array of front and front is incremented by 1. If the value of front and rear are equal, it means that there is no item to be removed and the value of both front and rear are reset to -1. Queues as linked list. Like stacks, queues can also be represented using linked list. Since the linked list do not have any restriction on its size, the queue can grow or shrink according to the insertion or deletion of elements. Each element in the queue should be represented by a node consisting of a data part and link part. This will be implemented by a structure in C++. A C++ program showing the operations of a queue is given below. Here the queue is represented as a linked list. Class queue, private, struct node, in data, node star link, star front, star rear. Public queue initializes data members, front equals null, rear equals null. Void insert queue of int item adds an element to the queue. Node star term equal to new node. If term equal to null, cout queue is full. Term data equals item. Term link equals null. If front equals null, front equals rear equals temp, return. Rear link equals temp, rear equals rear link. Int delete queue deletes an element from the queue. If front equals null, cout queue is empty, return null. Node star temp, int item, item equals front data, temp equals front, front equals front temp. Delete temp, return item. Queue deallocates memory. If front equals null, return. Node star temp, while front not equals null, temp equals front, front equals front link, delete temp. Void main queue queue. Q dot insert queue of 24. Q dot insert queue of 19. Q dot insert queue of 38. Q dot insert queue of -53. Q dot insert queue of 45. Q dot insert queue of 37. Q dot insert queue of -43. Q dot insert queue of 32. Cout item removed is Q dot delete Q. 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 Output item deleted is 24. Item deleted is 19. Item deleted is 38. Item deleted is -53. Item deleted is 45. Here the class Q contains a structure node which represents a node of the linked list and two pointers to the structure node. These pointers are used to keep track of the front and rear of the queue. At the beginning, the queue will be empty and hence both the front and rear are set to null. The insert queue function adds a new element at the rear. When the first element is added, both front and rear points to the new node. After that, rear will be incrementing with the addition of each new node. The delete queue function deletes an element at the front end of the queue. Removal of an item means the deletion of the node which is pointed by front. After the deletion, front is made to point to the next node in the list. When the program terminates, the constructor is called to release the memory allocated to the nodes in the list. Circular queues. In the array implementation of queue, a queue is reported as full if rear has reached at the end of the array, but there may be empty slots at the beginning. To deal with this difficulty, the queue can be implemented as a circular queue. In this arrangement, when adding elements to the queue and if reached at the end of the array, the next element will be stored in the first slot provided it is free. Hence, the queue will be reported as full only if all the slots in the array are occupied. The pictorial representation of a circular queue is given here. DQ. DQ is the short for double-ended queue and defines a data structure in which items can be added or deleted at either the front or rear end, but no changes are possible elsewhere in the list. In other words, the DQ is a combination of both stack and queue. A DQ is represented in the given figure. There are different methods of representing a DQ in a computer. The normal representation is with a circular array with pointers left and right to point to the two ends of the queue. The two variations of the DQ are input restricted DQ and output restricted DQ. An input restricted DQ allows insertion only at one end of the list but deletions at both ends. On the other hand, an output restricted DQ allows deletions at only one end but insertions at both ends. Before we conclude, let us summarize what we have discussed in this session. This module provides a brief description about the data structures called stacks and queues. The stacks are used more in function execution and recursion, while the queues are used to represent all the processes or jobs which are waiting to be executed. The stacks and queues can be represented using arrays or linked list. The module describes about the operations performed on stacks and queues such as push, pop, insertion and deletion. Certain applications of stacks and queues are given here. The module concludes by referring to the different implementations of queues such as circular queue and DQ. Before we attend the next unit, please try to answer the following questions. What is meant by a stack? What is LIFO? Why is it so called? Describe the implementation details of a stack as an array. Write a note on the linked list representation of a stack. Queue uses a FIFO structure. Justify. Here are some books for your reference. J. Glenn Brookshire, Computer Science, an Overview, 10th edition, Addison Wesley. Seymour Lipshot's Theory and Problems of Data Structures, Shor's Outline Series in Computers, McGraw-Hill Book Company. Yashwant Kanitkar, Data Structures through C++, BPB Publications. Hope you enjoyed the session. See you next time. Until then, goodbye.